Hello. In this podcast, we're going to take a look at the quantitative analysis of radial forces and circular motion. Specifically, we're going to do a little bit of review on what is the radial dimension and what is centripetal force. Then we're going to move on to examine how we determine the centripetal force, what happens to centripetal acceleration and force as the radius of the curve increases, what happens to the centripetal acceleration and force as the tangential velocity increases, and finally, how do we quantitatively analyze centripetal acceleration and force? Let's get started. First, let's just take a quick review of the radial and tangential dimensions. And here we have an object moving in a circular path, and I've shown it at 4 different spots. And so the radial dimension starts at the center of the circle or curve and extends through and past the object. The tangential dimension is perpendicular to the radial dimension and tangent to the object's circular or curved path. Notice that the dimensions move with the object. In other words, the intersection of the tangential and radial dimensions will always be in the center of the object. And so that intersection or origin moves as the object moves in the circular or curved path. The instantaneous velocity is in the tangential dimension, and the net force and acceleration are in the radial dimension, pointing towards the center of the curve or the circle. What is a centripetal force? And here we have 2 situations. We have a car going around a corner, and we have a game of tetherball going on. The centripetal force is the name for the unbalanced force or forces that cause an object to move in a curved circular path. Here with the car, and the car's coming towards us as it makes a turn to our right, there's this force of friction pointing towards the center of the curve, and notice it's unbalanced, so that's our centripetal force. Over here in the tetherball game, we know that the rope is keeping the ball in a circular path, but notice that it's not all of the tension force, it's just the x component of the tension force, because that's what's pointing towards the center of the circle, this horizontal circle that the tetherball is traveling in. This tension force, this vector arrow, is not pointing towards the center. The center of this circle is here. The centripetal force always acts perpendicular to the object's motion, and it is always going to point towards the center of the curve or circle. And most importantly, we need to think of the centripetal force as what it really is. It is the net force in the radial dimension. Okay, now that we did this short review, let's move on and learn about identifying and analyzing the centripetal force. So how do we determine the centripetal or net radial force? First of all, we have to recognize that because it's a net force in the radial dimension, the centripetal force is going to be equal to the sum of all the forces in the radial dimension. Now, in the case of the car, this is very straightforward in that there is only one force in the radial dimension. That's the friction force, and I've assigned a value of 2,000 newtons to it. So in this case, our centripetal force is equal to the net radial force. Well, there is only one force, the friction force, so that friction force is the net force in the radial dimension, and the centripetal force then is 2,000 newtons. Let's take a look at a roller coaster, and things get a little more complicated here. So let's look at this point where we're going over the top of a hill, and let's analyze the forces. We have a gravity force of 735 newtons, and we have a normal force pointing in the opposite direction of 300 newtons. So now how do we calculate the centripetal force? We have 2 forces in the radial dimension, and they're pointing in opposite directions. We need to recognize that forces pointing towards the center are positive, and forces pointing away from the center are negative. Now we can use this information to calculate the centripetal force, keeping in mind that it's the net force in the radial dimension. So we take the forces pointing towards the center, in this case the gravity force, and we subtract the forces pointing away from the center, and that's the normal force. So in this case, the centripetal force is 735 newtons minus 300 newtons, and our centripetal force is 435 newtons. It's very important to recognize that this centripetal force is neither the gravity force or the normal force. Rather, it is the net effect of the gravity force and the normal force. Now, let's keep moving on our roller coaster, and here we're upside down at the top of the loop. So let's look at our forces, and we have a normal force of the seat, and we're normally used to normal force pushing up on our seat, but we're upside down. So there's no way the seat of the roller coaster can push us up. It can only push us down. And of course, we have the gravity force of the earth pulling us down. And so I've put in values of 100 newtons for the normal force, and the gravity force on this person is 735 newtons. So how do we go ahead and calculate the centripetal force in this case? Well, we need to remember that the centripetal force is the net force in the radial dimension. So let's go ahead and add up the forces in the radial dimension, and because both the gravity force and the normal force are pointing towards the center of the circle, we're going to add them together. So the centripetal force at this point in the roller coaster is 835 newtons. Lastly, let's look at the bottom of the circle and calculate the centripetal force acting on this passenger. So we take a look at our forces, and we have the gravity force pulling down with 735 newtons, and we have the seat. This time the seat is exerting a normal force upwards of 1,500 newtons. And again, to calculate this centripetal force, we have to remember it is the net force in the radial dimension. So we go ahead and look at these forces, and we have the normal force pointing towards the center of the circle, and we have the gravity force pointing away from the center of the circle. So we're going to subtract the gravity force from the normal force. Remember, forces pointing towards the center are positive, and forces pointing away from the center are negative. So in this case, the normal force exerted on the passenger is 765 newtons. The biggest takeaway from these examples is that the centripetal force is not a specific force. Rather, it is the net force in the radial dimension. So in our roller coaster problem, we always had two forces acting in the radial dimension, and in none of these cases was the centripetal force equal to one or the other of these forces. Rather, it was the net effect of these two forces. At the top, it is the gravity force minus the normal force. In an upside down loop, it is the normal force and the gravity force added together. And at the bottom of the loop, it is going to be the normal force minus the gravity force. Let's move on. What happens to centripetal acceleration and centripetal force as the radius of the curve increases? Well, as the radius increases, the centripetal acceleration and force decrease. And here's why. Let's look at our semicircles down below. We can see the one on the left has a small radius and the one on the right has a larger radius. When an object travels the circle, the semicircle, from start to finish, notice that its velocity will change 180 degrees from start to finish. Now this change takes longer for the semicircle that's larger. Therefore, its velocity is changing more slowly, and that means a smaller centripetal acceleration and smaller centripetal force. So again, the object, as it travels around the circle, or around the semicircle, notice by the time it gets to the end of the semicircle, its velocity has changed 180 degrees. And the same thing happens with the larger circle. By the time the object gets to the end, its velocity has changed 180 degrees. So it's had the same change in velocity, but it took longer to have that change in velocity with the larger radius. And that means the acceleration is less, and therefore the force is less. Okay, what happens to centripetal acceleration and centripetal force as the tangential velocity increases? Well, now we have two semicircles of the same radius. And what happens is as the tangential velocity increases, the centripetal acceleration and force also increase. And the reason for this is, once again, both objects' velocities will change 180 degrees from start to finish, but the object that's moving faster will complete this change in velocity in less time. And that means a faster acceleration because the velocity changed faster, and that tells us, because of Newton's second law, a faster acceleration requires a larger centripetal force. So again, in this case, we have two objects moving through a semicircle. The one on the left is going 2 meters per second. The one on the right is going 5 meters per second. Clearly, the one on the right is going to get through the semicircle faster, which means its velocity changed faster and it has the larger centripetal acceleration and force. So how do we quantitatively analyze centripetal acceleration and force? Well, here are the equations. The centripetal acceleration is equal to the tangential velocity squared divided by the radius. And we can use Newton's second law to find the equation for the centripetal force. Newton's second law is simply the force is equal to the mass times the acceleration. So in this case, the centripetal force is equal to the mass times the centripetal acceleration, or mass times the tangential velocity squared divided by the radius. So let's take a look at a car that goes around a 25-meter radius curve. That means the curve has a radius of 25 meters, and it goes through that at a constant speed of 10 meters per second. What is the centripetal acceleration of the car? Well, we're going to use our formula. So we take the speed of the car, the tangential velocity, square it, and we divide it by the radius of the curve, which is 25 meters, and that leaves us with a centripetal acceleration of 4 meters per second. Now, let's find out how strong the friction force of the road acting on the car must be in order for the car to stay on the road. So we're going to use our centripetal force equation, and that's just the mass of the car times the centripetal acceleration of the car. So it's 1,000 kilograms times the 4 meters per second squared that we calculated in the first part. And that gives us a friction force of 4,000 newtons. Let's take a look at how we create force equations in the radial dimension using Newton's second law. So first, let's go ahead and bring up our two equations we have for circular motion. And in this case, since we're working with forces, we're not too interested in our centripetal acceleration equation, but we are very much interested in our centripetal force equation. And this is what we would call Newton's second law for circular or curved motion. Let's take a look at a roller coaster. And you're in between the first and second hills of a roller coaster ride. Your mass is 80 kilograms, your velocity is 20 meters per second, and the radius of the curve, the radius of this curve is 15 meters. How strong is the force of the seat pushing up on you? Well, all force problems need to start with a force diagram, so let's go ahead and do that. Curved motion is no exception to this. So we have our gravity force down, the earth pulling down on you, and we have the normal force of the seat pushing up on you. Because the center of the curve is above the track, we know that the upward force has to be stronger than the downward force. We can go ahead and calculate the gravity force because we know we're going to need that in calculating our net radial force. And in this case, the passenger U has a force of gravity of 784 newtons. Now let's take a look at our equation, and we're going to use Newton's second law to write our force equation. So the centripetal force is equal to the net force in the radial dimension, and we know that that is equal to the forces pointing towards the center of the curve minus the forces pointing away from the curve. And that is set equal to the mass times the tangential velocity squared divided by the radius. This portion here is our force equation in the radial dimension. We can go ahead and rearrange it to solve for the normal force. We can plug in our numbers, and we find out that the seat is pushing up on us with 2,917 newtons. At the bottom of the roller coaster, you feel heavier than usual because we feel the normal force, not the gravity force. And at the bottom of the hill, the normal force is 3.7 times greater than the force of gravity. So when you're just sitting in your chair in the classroom, the normal force of the chair pushing up on you is equal to the gravity force. So that's what you're used to feeling. But now at the bottom of this roller coaster hill, the normal force of the chair, of the seat pushing up on you, has to provide that centripetal force to keep you in curved motion, and it is much stronger than you're used to feeling. In this case, 3.7 times stronger. Another term for this is you feel 3.7 G's of force, and you'll often hear roller coasters advertised based on the G's of force you feel. If you have studied aviation, you'll hear about fighter jet pilots and the number of G's of force that they experience when they go through a tight, fast turn. The formula for calculating the G's of force is simply the normal force divided by the gravity force. The important takeaway here is that when you're analyzing forces in curved or circular motion, you still need to do a force diagram, and you still use Newton's second law to set up your force equation. It's just that for curved and circular motion, Newton's second law has a little different twist to it, in that instead of mass times acceleration, it's going to be mass times the tangential velocity squared divided by the radius. Let's move on and take a look at circular orbits, because in circular orbits, gravity acts as the centripetal force. So gravity causes orbits. It causes the planets to orbit stars. It causes the moons to orbit planets, and it also causes satellites to orbit Earth. Here is a picture of a satellite orbiting the Earth. Clearly this drawing is not to scale. But let's take a look at a few important things. We see that gravity is acting towards the center of the Earth, and we know Earth's gravity is always acting towards the center of the Earth. This dashed circular line, this is known as the orbital path. This dashed line is the radial dimension, and this dashed line here is the tangential dimension. Notice that the gravity force lies on the radial dimension, and it is unbalanced. It is the only force acting on the satellite, and so the gravity force fits our definition of the centripetal force. Now, I want to point out orbits are elliptical, but most are nearly circular. So we're going to treat this satellite orbit as being perfectly circular. Also, just as a point of information, while Earth's orbit around the Sun is elliptical, it is nearly circular. In fact, if you looked at the Earth's orbital path drawn to scale, you would think it was a circle. You would not be able to tell that it was elliptical. Let's look at a few key terms and relate them to some of the key terms we've learned about circular motion and centripetal force. First, we have the orbital velocity, and it is the tangential velocity of the object because it's moving in the tangential dimension. Next, we have the orbital altitude. That's the distance between the surface of the planet or star and the object. In this case, the orbital altitude is the distance between the Earth's surface and the satellite. Not to be confused with the orbital altitude is the orbital radius, and that is the distance between the center of the planet or star and the center of the orbiting object. In this case, it's the distance between the satellite and the center of the Earth. Let's discuss a few concepts about circular orbits before we get into the quantitative analysis. So conceptually, we have to recognize that the gravity force gets weaker as objects move away from the center of the planet or the star. For instance, Earth's gravity is much stronger on the surface of the Earth than it is if we're hundreds of thousands of kilometers away from the surface of the Earth. And because the strength of the gravity force is a function of how far you are from the center of the Earth, each orbital radius has a unique fixed gravity force. And this is determined by Newton's law of gravitation. We're not going to get into that in this unit. We will cover that in our unit on gravitation. Therefore, each orbital radius has only one possible orbital velocity. Satellites that are orbiting about the same distance above the Earth's surface are all going to be traveling at about the same orbital velocity. Finally, the orbital velocity decreases as the orbital radius increases. So satellites that are orbiting further away from the Earth are going to be moving slower than satellites that are orbiting closer to the Earth. Let's get into the quantitative analysis now. And of course, we're going to use Newton's second law, adapted for circular motion. And that is the centripetal force is equal to the mass times the tangential velocity divided by the radius. And let's just be clear, in this case, the gravity is the centripetal force measured in newtons. The object's mass is the mass in kilograms. The orbital velocity is the tangential velocity in meters per second, not kilometers per hour or kilometers per second. And the orbital radius, not the orbital altitude. The orbital radius, not the orbital altitude, is the radius in meters, not kilometers. So there's two things when dealing with this R. First of all, you want to use the orbital radius. That's measured from the orbiting object to the center of the Earth. You do not want to use the altitude because that's measured from the surface of the planet to the satellite. And also, because these distances are so large, you will usually be given the orbital altitude or orbital radius in kilometers, but you must convert it to meters when you use it in the equation. Let's go ahead and solve a problem. So in this case, we have GOES 16 is a 2,857 kilogram weather satellite that orbits Earth 35,786 kilometers above the surface. So that's the orbital altitude. Now we need to add the radius of the Earth to get our total orbital radius. And when we do that, we get 42,157 kilometers, and that's because the Earth's radius is 6,371 kilometers. So we add the 6,371 kilometers to the orbital altitude, and that gives us the orbital radius, which is measured from the Earth's center. The gravity force acting on the satellite at this altitude or orbital radius is 640 newtons. So in part A of this problem, we're asked to find the satellite's orbital velocity. So we're going to take our Newton's second law and we're going to rearrange it to solve for the tangential velocity. So we go ahead and rearrange it, and then we plug in our gravity force. We convert our orbital radius to meters, and we divide it by the mass of the satellite, and we take the square root of that result, and we find out that the orbital velocity for this satellite is 3,073 meters per second. That's about 7,000 miles per hour. Part B, how long does it take to make one orbit? And here is an important hint. We need to remember that the circumference of a circle is 2 pi r. So even though we're talking about a circular orbit that's huge, it's still a circle. And so the length of this orbit, or the length of one orbit, is 2 pi r. Also, we need to recognize that the amount of time it takes to make one orbit is known as the orbital period. And so the formula for the orbital period, capital T is the symbol for the orbital period. It is equal to the circumference of the orbit divided by the tangential velocity. And of course, we know the circumference is 2 pi times the radius. And now we go ahead and plug in our orbital radius in meters, and in the denominator we put our orbital velocity that we calculated in part A, and we find out that it takes 86,196 seconds to make one orbit. That's not too meaningful to me in seconds, so I always convert this to hours, and it's 24 hours. This satellite moves around the Earth at the same rate the Earth spins on its axis, because the Earth makes one complete rotation in 24 hours. When the satellite is revolving around the Earth at the same rate the Earth is spinning, we call that geosynchronous orbit. If this orbit is above the equator, and in the case of the GOES 16 it is above the equator, we call that geostationary. In other words, that satellite is going to be above the same spot of the Earth all the time, because as the Earth is spinning, the satellite is orbiting at the same rate. Well, that's just an interesting fact about satellites. There's all different types of satellites, and based on their function, they'll orbit at different levels. There's 3 general classifications. There's low Earth orbit, there's medium Earth orbit, and there's high Earth orbit. Our weather satellites and communication satellites are in what's called high Earth orbit. GPS satellites, on the other hand, are in medium Earth orbit, so they would orbit closer to the Earth than a weather or communications satellite. This wraps up our lesson. In closing, let's summarize what we've learned about quantitatively analyzing radial forces and circular motion. Centripetal acceleration is in the radial dimension. It's a measure of the rate at which the velocity's direction changes. It's not a measure of how the magnitude of velocity changes. And we can calculate the centripetal acceleration using this equation. Closely related is the centripetal force, because it is the unbalanced force that creates the centripetal acceleration. So it too acts in the radial dimension. It is not a specific force. It's important to remember that it is the net force in the radial direction. And we can calculate this net radial force by taking the forces acting towards the center and subtracting from them the forces acting away from the center. And finally, we can use Newton's second law, adapted for circular motion, to create force equations to analyze radial forces. Well, that ends our podcast. I hope this helped, and have a good day.